Welcome everyone to our online seminar. Hopefully sometime this year we'll be able to do away with those. We have today remotely with us Greg Ashton from the United Kingdom. He's currently a fellow at the Royal Holloway just outside of London, and concurrently with a position at Monash University, Australia, and the collaboration OzGrav, which is a big Australian gravity collaboration you should probably be aware of. He did his PhD and undergrad work at Southampton University, then a postdoc at the Albert Einstein Institute in Hanover, Germany, and then had a position at Monash, which he continued into England. Take it from here, Greg. Good luck.
Excellent. Thank you so much. And hello to everyone. Nice to meet you virtually. I also say it's wonderful that people have their cameras on. That's super useful for me to see if people are sort of, falling asleep and I should speed up or confused. So yeah, feel free to jump in at any point and ask questions as we go through. I will try and watch the chat, but I often struggle with that. So it's easiest if you just open your mic and start talking and stop me. Don't wait for a pause because I have a terrible habit of just talking too much. So okay, so this is some work on the Vela radio pulsar, and in particular, a glitch in that object. So as Ofek mentioned, I'm part of the OzGrav collaboration, and most of my work is to do with, nowadays at least, is with CBC inference. But I know you're all, many of you are sort of experts in this already and have lots of experience. So I thought I'd talk about something a little bit different today. So first up, if you haven't heard already of what a pulsar is a neutron star. So it takes something like the sun, end of its lifetime, it goes to a supernova, collapses down, and you end up with a very, very dense ball of nuclear matter, about 10 kilometers across or so. And what's really fascinating about them is that they have really very strong magnetic fields. And these magnetic fields, as I'll show shortly, produce a nice beam of radiation. And that beam of radiation then, as the neutron star rotates, causes a sort of lighthouse effect, which if this animation works, what you end up seeing if you, in the line of sight as that sort of lighthouse passes over you, is a pulse of radiation. Now, that's why we call them pulsars, of course. Now, and of course, we see a huge variety of them. This is just one sort of particular animation showing what they sort of typically look like. So that's your basic introduction to pulsars there. Now, how does that work? What's the real physics behind it, and how do we get into that? Well, as a sort of very basic model, you have a dipole, which is fixed in the rotation frame of the neutron star. And that is, of course, misaligned with the rotation axis. Of course, if it's along the rotation axis, then you don't see pulsations. So it needs to be, we know it's misaligned in order for us to see the rotation. Now, that it is misaligned and that there is a dipole being rotated through, a dipole being rotated means that you end up with an electromagnetic torque on the pulsar, which slows the pulsar down. Now, of course, there could be other torques, and one of the things which I'll talk about a little bit later on is the continuous or a gravitational wave torque. If the neutron star is not completely spherical, then you will get gravitational wave emission, and that can also slow the star down. Of course, we haven't actually seen that. That remains yet to be seen, and for all the radio pulsars that we know, the dominant emission mechanism at least seems to be this electromagnetic torque. So I put in my title this term glitch, and I want to be very careful here. I'm going to refer to it as a radio pulsar glitch. I see something, okay, excellent. Thank you, Ofek, for the translation there. So I know that if you have had any experience with LIGO or ground-based gravitational wave detectors, then you will be aware that there are things called glitches in our gravitational wave detectors. Nothing I say today has any relation to those glitches. So those are a purely sort of instrumental artifact which happen in gravitational wave detectors and nothing to do with what I'm talking about. So what I'm talking about is glitches in radio pulsars is a phenomenon which happens periodically, well, spontaneously, and over timescales of hundreds of days to even thousands of days. The phenomenon itself can be roughly understood as this. So as the star rotates, you see these pulses, and from that we can measure very accurately its rotation frequency. As that torque applies to the star, it starts to spin down. And so what you see is, of course, the frequency of the star decrease. That's the sort of initial part. You just get up the, I've lost the thing where you can you see the pointer on here? Okay.
Yeah, we see
Yeah,
it.
it's not excellent. So this here is the sort of, yeah, this is regular spin down, right? This is just an electromagnetic torque spinning the star down. And then what you see is all of a sudden, the star suddenly increases its rotation frequency. And this can be quite significant. So it can happen up to 1 part in a million or so. That may not seem very significant by itself, but you have to imagine here that, you know, you're rotating, you know, about a solar mass in a sort of 10-kilometer ball, and doing that, you know, every few seconds or so. So an increase of 1 in 10 to the 6 means you've moved a huge amount of mass around, or you've affected the moment of inertia in some way in order for it to spin differently. So this was first seen almost a year after pulsars were first observed, and in fact it was seen in this pulsar called the Vela pulsar, which is a very near pulsar and so very easy to study. Now, there's a lot of different models of what might cause this. There's 2 competing ones, and the one which is, I guess, most favored and people generally take to be the kind of canonical model is a 2-component model. So what theory tells us is that a neutron star is not, of course, just one uniform type of matter, but rather you have lots of sort of shells within it. So you have an atmosphere, as I'm showing here. That's not so important for us. What's important for us is that you have something called an outer crust, which is perhaps a few hundred meters or so thick. And then you start to have things like the inner crust and perhaps some sort of core inside of that. Now, each of those components can be quite different. And the way that we try to figure out what they look like is doing sort of numerical studies in which you simulate, you know, very dense quantum matter at the sort of densities that we find inside neutron stars. Now, what's thought is that the inner crust is likely a superfluid neutron layer, and so what happens is this superfluid neutron element rotates independently of the outer crust, and so the inner and outer crust, at least when we generally see pulsars, are not coupled on short timescales. They may be coupled on much longer timescales of say months to years or so, but they're not coupled on a few seconds timescale, for example. What this means happens is that the electromagnetic dipole is, of course, the torque is acting, and it acts predominantly on the outer crust layer. And so when we see the pulsations from the star, we're really tracking the outer crust of the star. If you like, we're measuring the phase rotations of that outer crust. So they say the inner crust can then be decoupled from that outer crust, and the inner crust feels much less of a torque. What this implies is that the outer crust will spin down faster than the inner crust. So what ends up happening is you end up with a differential rotation between the outer and the inner crust. Now, at some point, that difference in rotation rate builds up to an appreciable fraction of effectively a coupling constant, which we don't know quite yet. And as soon as that happens, the two all of a sudden couple together. And of course, the inner crust is spinning faster than the outer crust. And so if you're just looking at the outer crust, as we are, what you see happen is the outer crust suddenly spin up, and then the two couple together, and you get back to sort of regular rotation. And on some longer time scale, the two decouple again. Now, the timescales of this happening are, the timescales of glitches are something like a few seconds or so. And we'll talk about how we measure that in just a moment. The timescales between glitches are typically of order of a few years or so. Now, there's a few kind of subtleties to all of this. So, of course, you'd really like to use this model to try and infer something about neutron stars themselves, right? So these are cosmic laboratories where you have matter in a state which we almost certainly can't get to in any terrestrial laboratory. It's at very high pressure but low temperature. And so by studying radio pulsars, we can try and figure out what the state of matter is in these neutron stars. And how do you do that? Well, you take your model, which I just described, of what the neutron star looks like, and you fit it to your observations. Now, unfortunately, so far, although we've had many glitches, they haven't been entirely compelling as to which particular model fits everything. The best model we have so far is this two-component model. It seems to explain most things. There's a few things which are currently, not yet understood. The first of them is what we call the sort of lag time between glitches. So the model which I just described to you of having something, the outer shell spin down, the inner shell sort of be decoupled, and then the two coupled together, should tell you that, if that was really happening, it's a little bit like, filling water up into a jug or something like that with a constant rate and then tipping it out. You'd expect it to be a kind of periodic process, right? Like you decouple them, the outer layer spins down. Once it gets to a sufficient lag, then couples, the whole process repeats. Unfortunately, there's only about 2 pulsars which show some element of real periodicity in the waiting times between their glitches. Most others show a Poisson process. And this doesn't quite fit with this simple model. So people modify it in all sorts of ways. They have sort of vortexes which creep around and all sorts of interesting ways of modifying this. But okay, so that's the background to all of this. That's what radio pulsar glitches are. And what I want to tell you about in this talk is a particular observation.
We have a couple of questions.
Oh, sure, yeah.
The first,
there's the chair.
First is my own. I'll ask if you expect the inner core to be spinning at a fixed rate because it's not slowing down due to torque. Wouldn't you expect the resumption of the slope of the outer part basically to always start at the same frequency or go down to the same frequency or match its frequency to the core?
So they have, so it depends obviously on the fractions of moment of inertia of one to the other. And that's something that we don't know. So certainly if the inner was much, much larger and, effectively, when they coupled, didn't get spun down, you would expect them to both, always go up to the same frequency. Now we don't see that. So that then tells you that the moment of inertia of the inner part, which it couples to, has to be, at least, maybe a few hundred times at most bigger than the part which we see, the outer crust. So what happens when they couple is that the inner part gets spun up, the outer part gets spun up and the inner part gets spun down. So you get a kind of matching between them, someplace in the middle. Where that happens, as I say, depends on the fractions of moment of inertia each one takes up.
Okay, the other question a student asked here privately, so I'll share it publicly, is what is a Poisson process?
That's a very good question. Sorry, I assumed knowledge there, so thank you for asking that question. So Poisson process means any kind of process where the waiting times between events are, let me get this, I want to make sure I get this right and so I don't confuse people, are not correlated. So a good example of this is something like buses. So if if buses try and come at a sort of fixed schedule or something like that, then yes, that's correlated. If you see one bus come, then the next one will come 10 minutes later. But imagine instead that buses just start out from the depot at some random time, get lost in traffic, and then you wait at the waiting stop there, and you wait for buses to come. They will be Poisson distributed in that if you see one bus, you've got no idea if the next one is coming sooner rather than later. And I guess a more typical process is something like radioactive decay, where you have a half-life, something like that. So that's again, that's a more typical Poisson process, I guess, for physicists. I don't know if Opek wants to add anything on Poisson processes.
No, just that I guess one way of putting it is no correlation, and otherwise calling it no memory. right? They're memoryless processes. So if you just arrive at if you just start your detector for nuclear decay, for example, radioactive decay, then the time you'll wait until you measure the next one is completely independent of anything that happened before, or particularly when the last one arrived. And if you just measured one, then you can maybe just measure one again. It doesn't matter. Every nucleus decays independently of all the others, so they're uncorrelated. They have no memory. You don't know what happened. They can come in bunches. They can come spread out. All you have is kind of this mean time in between. And if you sum up the amount of clicks up to at any point, you get what's called a Poisson distribution.
Very nice.
Greg,
Okay.
I have a question also.
Yeah.
What about a white dwarf pulsar?
Was that white dwarfs?
Yeah, I heard that there were some detections of white dwarf pulsars.
Yeah, so we see, in fact, we see many white dwarf binaries within our own galaxy. And so in terms of compact objects, we have three which are, which are interesting, and which, so when a star goes supernova and collapses, there's three different, well, there's actually I think maybe a handful more that I'm not aware of, but in terms of my own experience and knowledge, three compact objects that they can form. One is a white dwarf, which is the largest of the few. Then you have a neutron star, which is smaller, and then you have a black hole, which is if they collapse entirely. And each of those, whether you get one or the other, it depends on the amount of matter that you have in the explosion and how much is sort of left over, and whether you're going to, whether a new physical process is going to provide the pressure, the outward pressure to keep it sort of stable. So with a neutron star, you have degeneracy pressure, which is keeping things nice and stable. I'm actually now blanking on what the white dwarf degeneracy pressure comes. OPEC's going to save me, I know.
The white dwarf is also degeneracy pressure, but it's electron degeneracy.
Yes.
And the neutron star is neutron degeneracy.
So
and
my question is
the factor there of 2000 in the mass is basically giving you the is related to the factor in the radius and all the other stuff.
But my question is regarding like the picture of the model of the shells. If it's not a neutron star but a white dwarf, so this picture is not relevant, no?
Oh, absolutely, yeah. So the things that I'm talking about are going to be radio pulsars, which we know have to be neutron stars because of the rate that they rotate. You just cannot get if you rotated the white dwarf at that speed, it would break up. So the only thing that can rotate at that speed and have a magnetic field which produces radiation is a neutron star, because your black hole can't do that.
Okay, thanks.
This is actually a calculation you can do on the back of an envelope or in your head. Take the rotation period, which can be order of even 10 milliseconds or something of the order of that, and put in the radius that you can measure or estimate from the magnetic field conservation or any other estimate of the radius or the mass that you have. Try to squeeze down a solar mass to spin at that velocity, and you'll have a bound on the centrifugal force at the edge of the star. And of course, the centrifugal force goes like omega squared r. So if omega is something that you measure from the rotation, and the mass from, say, if it's a binary system or any other measurement of the mass, then the wider the star is, the bigger r is, the stronger the centrifugal force. It has to be bound by gravity, so it doesn't break apart. And so you find that basically the radius has to be very, very small to spin a solar mass at that rotational velocity. That's so fast. You get something like the order of 10 to 20 kilometers for the radius. It cannot be any bigger than that. And if you take a solar mass and squeeze it down to 10 or 20 kilometers, you get to densities that are basically nuclear densities. So that's where the distinction comes from.
Excellent stuff. Any more questions? if not, I'll move on, but I'm enjoying the questions, so do keep them coming. Okay, so that's glitches. So glitches are when we see the star suddenly increase its rotation speed. Now I've mentioned one model of that, which is this coupling between different components of the star. I want to mention briefly the other model, which is out there and often used, but largely being sort of discarded as a model for explaining all glitches. It could still explain some, but as I'll say, it doesn't sort of have the right characteristics to explain all of them. So the other model is what we call starquakes. So the idea is if you take a fluid ball and you rotate it, then you will, of course, have, as Alfred was just saying, a centrifugal force. And so you will then, I can imagine your star being sort of oblate, something like this. Now, if you then freeze that and make it a solid, and then gradually slow the star down, then its reference shape, i.e. the shape it would like to be if it was fluid, is going to get sort of less and less oblate as the star slows down. So what you end up with is a tension between the shape of the star as it is, which is quite nice and oblate, and the shape of the star as it wants to be, which is less oblate and more spherical. And that ends up with this, you build up strains effectively, and the idea is that builds up, those strains build up until they fracture, the whole star collapses inwards and spins the star up. And that's, as I say, what's known as a starquake. I saw a question pop up, but I can't get the thing to, there we are.
Another translation.
Okay, excellent, thank you. So the reason that we know that those can't explain most glitches is simply a timescale argument, that we know sort of how oblate it would have to be, and well, we know how oblate it was at birth, and how much it sort of gets, if you like, how much that shape changes between glitches, and we know that can't build up enough stress to explain the timescales that we see. So it's purely a timescale issue, that they don't spin down enough to explain the size of the glitches which we see. They could still be involved though, and I'll say more about that when we get a bit of a more detailed model later on. Okay, so now I'm going to get onto this particular glitch which I want to talk about. So in 2016, the Vela radio pulsar underwent a pretty large glitch, and it was observed by this telescope down in Tasmania in Australia. So it's the Mount Pleasant Observatory, and this is a pretty special telescope, not because of its size or how good it is. It's actually a pretty small dish relative to some of the things like the Parkes and George Bank dishes that people typically talk about. And even in for the fast and other sort of huge scale things. So well, what's exciting about this dish is because it's smaller, the university which owns it, which is the University of Tasmania, decided that what they would do with it was, rather than try and compete with these bigger dishes, they would use it entirely to surveil the Vela pulsar. So that all it does is this dish just tracks the Vela pulsar continuously. And the aim of this always was to catch the Vela pulsar during a glitch. And in 2016, this is what they managed to do, and they recorded the first pulse-to-pulse observations of a glitch. Now, something I should mention here is how pulsar timing actually works. So when we talk about pulsar timing, almost no pulsar other than Vela has this happen to it, where they watch it continuously. Oftentimes you can't even watch them because they dip below the horizon at certain times of the year. This is a very special pulsar, and this is a very special dish in that it can do this nearly continuously. So what happens typically is we point our dish at a particular pulsar for about half an hour to an hour once a month, or some time scale like that. They, of course, there's many details, and you have to go and get the ear of whoever owns the dish in order to get some more observing time. But that's generally how pulsar timing is done. Is we look for half an hour or so, in this week, and then 4 weeks later we look again for half an hour, and that's pulsar timing. So when we say we've seen a glitch, what we really mean is, well, we looked at it in January and it was going at this rate, and then we looked at it in February and it had sped up, and that's how we know that there was a glitch, and we know that it happened sometime between those. Now, because we have many different observations, you can usually narrow the time down of the glitch. And indeed, people had managed to do this to within sort of minutes before this observation. But this was the first time that we'd actually seen the glitch in action, so seen every single pulse. This allows you to do something really pretty cool, which is to actually see the rotation speed of the star increase in real time, if you like. So this plot on the left here is so from our paper when we looked at the dynamics of this glitch. And what you're looking at is the offset in the rotation frequency from the pre-glitch rotation frequency. So of course, to measure that, we're looking at individual pulses. We have to average over some baseline, and we average over about 100-second baseline. So there's a sort of 100-second smearing going on here. Okay, so be wary of that, and I'll talk about why that's important in a second. But what's really interesting, right, is that you see just
what's a single period for this pulsar?
A single period is 0.11 hertz. Terrible.
0.11 hertz, so 9 seconds.
No, sorry, my brain is. Give me 1 second. I want to get this right, and I seem to be having a real problem today with my. Are you still seeing the slides, or are you seeing my Google?
No, we see the slides. We don't see you Googling during your talk.
Excellent, because I know this number, but it's one of these things that has just, I don't know, it's dropping out of my brain. It's 11.1 times per second. So the period, sorry, is 11.1 seconds. Sorry, 1 over that. So that's the frequency.
Oh, so like 0.09 hertz?
Yeah.
Okay, so 100 seconds, you're doing about 90, or 9 periods.
Hang on. Yes, yeah, about 9 or 10 periods within that 100 seconds.
Okay.
Yep. So so we're seeing a smearing here with that process, and that's something, as I say, to keep in mind. So when you look at this graph, you see just before the glitch happens at t equals 0, of course. Now before you see it's at an offset in frequency from the 11.2 hertz or so of 0. And then afterwards, we see it's clearly increased its rotation frequency by about 1.8 times 10 to the minus 5 hertz. Now, you see there a kind of ramping up effect, right? So you see the frequency increasing, but this is where you need to be careful, which is that smearing is broadening that out. So if you take a square wave and you convolve it, with a sort of moving average, you'll get a sort of nice sort of function which smoothly goes up and down and has some width to it, and that width depends on your averaging box. So you can't use this graph on the left to measure the rise time of the glitch. And in fact, you have to be very careful when interpreting any features in this because of this smearing effect. So there's 2 features which sort of stand out, which is if you look just after the glitch, it looks like it kind of overshoots. So you get an increase in the frequency and then it comes back down. It's hard to explain that with as an artifact of the data processing, but it's also hard to say whether it, shot up and then came down very quickly, or it was something sort of average in that. It's, again, you have to be careful that there's this averaging process going on. And before the glitch, you also see that the largest excursion downwards happens just before the glitch, and that's a little bit sort of interesting. So what this plot does allow you to do is to see this in sort of a smeary detail. But what we wanted to do, of course, was to analyze the dynamics without any sort of post-processing being applied to the data. So what we did was we fitted models to the data, which don't use this averaging process. We fit models directly to the time of arrivals of the pulses themselves. And I'll say a little bit what that means later on when we get into what may be going wrong with this process. But by fitting models, you can, of course, start to infer some interesting things. So the first is you can infer the glitch rise time. And so this is this plot on the right here. And you can see that the 90% credible level gives you a glitch rise time of about 13 seconds or so. It peaks at 0, so we're not resolving the rise time. It's below the sort of the level of our data can tell us it's below our resolution. but we're constraining it at 13 seconds, which is the tightest constraint anyone's made on one of these. Now, that in itself is interesting because, of course, with the models which I sort of mentioned to you earlier, these sort of coupling models, what this rise time tells you is what the coupling coefficients are between those two components. And so that starts to tell you things about the superfluid component itself. Now, okay, so that was sort of using the models to do things. Now, I want to talk a little bit about what the original detection paper did. So that was our work, which was looking at the dynamics. But this was a follow-up to the original detection paper, which was Jim Palfreyman and others published in Nature. And they were actually looking at it in a sort of different angle. And this is the title of this whole talk was The Deepening Mystery. And this is going to be the first mystery. And I'm going to go through now a whole bunch of different things that we don't understand about this glitch. What we've seen so far is what we do understand. So when Jim went and looked at this data, of course, he's very excited by it and studied through it. What he noticed was that there was what was called a null just before the glitch. So on the right-hand side here, what I'm showing is a series of pulses observed for this pulsar. They're labeled. The numbering doesn't have any significance at all. 0 doesn't mean where the glitch is. The glitch comes sometime after this at about, I think it's rotation 150 or something like that. No, sorry, it must be about 100. So anyway, though, this is the raw data itself that you're looking at. Now, when you look at when radio pulsar people show you pictures of their data, they'll typically look a lot better than this, and they'll look more like this plot at the bottom here, which says the integrated pulse profile. And that's typically what radio pulsar astronomers do, is they take the individual pulsations over their half-an-hour observing period, and they stack them down to get a single integrated pulse profile. The reason to do that is it's simpler, and most of the interesting sort of timing and things that they're interested in is better measured by their integrated pulse profile. So individual pulses, as you can see, vary significantly in any given pulsar. But when you stack them down, you get this really nice sort of smooth integrated pulse profile. And with that, you can do all the timing and things that you want to do. But of course, this is a glitch and we've caught it pulse to pulse. So we don't need to do that, right? We can look at the individual pulses themselves. And this is what Jim started to do. What he noticed was that this pulse here, pulse 77, is what's called a null, which is that there is no pulse there, or at least no pulse which you can pick out by eye, and certainly our sort of algorithms which go and test for whether something is a pulse or not tell you that there's really nothing there whatsoever. Now this is super interesting because the Vela pulsar doesn't null. A lot of pulsars do null. They sort of go in and out. But with the Vela pulsar, it's never been seen to null before this. And so you have two very interesting phenomena, very coupled very closely in time together. So the glitch, where you're expecting that components of the star are suddenly locking together and increasing their rotation speed, and a null, which is when the magnetosphere apparently shuts down and doesn't produce any radiation for the 0.1 seconds or so, 0.2 seconds if you take the either side of the null as well, as the sort of rough time scale.
Greg?
Yeah.
Another question. You said that if we are judging by eye, so 77 is not showing anything, but also 76 might be from the same sort because all the others have like a really good visual spikes.
Absolutely.
So how do you categorize 76?
So 76 absolutely was categorized by Jim and others as an unusually broad pulse. It definitely stands out. Again, if you do a sort of statistical analysis, this isn't a standard pulse, and the fact it happens just before the other one tells you, okay, maybe you have some sort of picture in your mind of the magnetosphere. Maybe it's sort of shutting down, broadens out in sort of 76, 77, it's completely gone, and then back on in 78. And some other weird behavior happens just after it as well. You get sort of the polarization of the light, which they can measure, also seems to change. I don't quite understand what that's telling us either, but there's definitely some funky business going on around that in terms of the beam itself. Now, I think this
Must
is,
be aliens.
well, I mean, there's a lot of people who make those claims, yeah. But I think this is really fascinating for the neutron star community, the theory community, because we've been seeing glitches now for 50 years, and there's almost as many papers on the theory of these things as there is glitches. There's about 2,000 or 3,000 glitches, I think, that are known. No, sorry, maybe 10,000 or so, a few more than that. So, but what's really interesting, right, is that we're now connecting two completely different parts of the star, which previously people really haven't had a good model of what the magnetosphere is doing, and if it has any effect on the glitch whatsoever. People have done studies of the pulses before and after glitches, but they've never been able to catch it during it, and so no one's seen anything like this before. So this really sets up a challenge to the theorists to go away and build me a model which has a null and then has a glitch, right? Like, what causes that? So
wait, what's the width of each of those boxes?
Those are, I'm gonna look it up for you. I think they're about 2 or 3 milliseconds.
Oh, so the glitch is milliseconds long and like 10 seconds apart.
Yeah, they're very narrow. I cut that off, didn't I, when I cut and pasted this in? Yeah, so it's 5. So the two ticks at the bottom are -5 and +5 milliseconds. You're looking at a 10 millisecond period there.
Okay, thanks.
Okay, so what have the theorists got for us? Well, Ashley Bransgrove and some folks working with him came up with, I think, the first kind of complete model which explains this this null and this glitch altogether. And the model effectively goes like this. So they effectively say, well, based on the time scale of it happening and the fact that you have this interaction between the two, there's no way that the glitch itself can be a crossquake. The size of the glitch tells you that it has to be one of these superfluid unpinning events where you suddenly couple the inner and outer parts of the star together. But maybe what triggers that is a crustquake. So their model is essentially that a crustquake occurs somewhere within the inside of the star. So you have some sort of breaking of a plate or something like that. That itself doesn't cause the glitch, but it's enough to cause, effectively you get alpha N waves coming out, which then travel out into the magnetosphere and cause this, what they call quenching event. And they simulate this numerically, and they show that this does produce what we expect, what they think it should do, which is that the magnetosphere effectively turns off for about a rotation period or two, and the time scale of over which the glitch happens. Sorry, the time scale over which the crossquake happens tells you that it has to happen very deep inside of the core itself.
You're gonna have to explain alpha waves now.
I am not well placed to do this in the context of neutron stars, I'm going to be honest. I'm still trying to wrap my head around this model myself. Afik, do you want to say something about them?
I'm going to recommend to the students to take a SAF's plasma physics course in the next year. It's a phenomenon that happens in plasma. There are all types of waves which mix, I guess, electric, magnetic, and hydrodynamical phenomena and couple them together. And these are the type of things that make these systems complicated and interesting. Yeah,
sorry, I don't have a good explanation. It's something that's always been on my radar of a word that I know, and I know roughly what it does, but I certainly have yet to have a good sort of intuition about what's really going on with the model itself. Okay, so so this crossquake causes, effectively, in simple terms, that the crossquake disturbs the magnetosphere, and that causes this the magnetosphere to shut down, which causes the null. But then equally, it also triggers the glitch. So the crossquake is sort of connecting these two things in this manner. So this is a nice explanation, and it seems to fit with at least the observations which we have in hand. Now, that's the first mystery perhaps solved. Perhaps the null is due to this model. Now, I have to say it's early days, and I know that there's other papers out there and other people out there who are coming up with different models to explain this. So I don't think we've heard the last of these models yet, but that's an evolving field in and of itself. Now, here we get onto the second interesting mystery of this glitch. So, as I mentioned earlier, what we did is we went and studied the dynamics of the glitch. We ignored the null and said, okay, the null seems to be happening. We don't understand what's going on, but we have this wonderful data set which tells us about the rotation speed of the star. So we can use this to model the dynamics of the star during the glitch. And so you can imagine fitting, phenomenological models of the rotation frequency. So, the most basic is you have a sort of step function in the rotation speed and fit that to the data. And of course, that's one model. And then you sort of modify it and you have some sort of rise time. And you keep playing around with this, inspired by physics, which is out there in the literature, but sort of, in some sense, we were data-led, which is a little bit dangerous. And I'll speak as to why in just a second. But fitting these models, what we did find was overwhelming evidence for this overshoot. So on the right here, what I'm showing is a plot of the gray line in the background is this smeared out rotation frequency plot, which I was showing you before. And overlaid on that is the best fit models that we found. So two of them. The first has a sort of, so you have a step function in the frequency, but then this has an overshoot and a decay. Now, as I say, this is a purely phenomenological model, but it was inspired by models which are out there in the literature. And in fact, the main sort of model which is out there, which was from our collaborator, Vanessa Graeber, is that if you have more than one component in the star and those interact, you would expect, in fact, to have an overshoot. So you have a superfluid component. Sorry, the Zoom thing is covering up my screen. Okay, there we are. So you have a superfluid component, which is the outer core, if you like. You have an inner core, which is labeled A here. The B is then the superfluid component. And then you have an outer shell, which is the observed component C. And if those are set up in the right order, which is, according to Vanessa's model, the order you should get, then you end up with this overshoot happening. So you get a rise in frequency and then a fall off. And this is, as we saw, seems to explain the observed data. So we fitted a model, a phenomenological model, which had all these features. And that seems to be a pretty good fit to the data and had pretty overwhelming evidence. Now, this is powerful because it allows you to start measuring moments of inertia and coupling components between those various bits. And so there's two papers there which have gone into doing this in quite a lot of detail since then. So
Two
we
questions.
seem to
Two questions. One, I see here that a glitch basically ends with all three components spinning together.
Yep.
Does that happen in the two-component model as well? They spin together?
So at the end of both models, they are all spinning together, but then they decouple and they're effectively sort of, I think it's some sort of hyperbolic time. They just kind of decouple and no longer interact.
Okay, and another question is there a physical simple reason to understand why a third component creates an overshoot, or is it just we added one more parameter, so now we can do more things phenomenologically?
So we know that there are more, well, theory tells us that there should be more than one component in the star. So we have that going for us. But as soon as you add another component, you've added, okay, not just one more free parameter, but in fact, a few more free parameters. And it's really about the fact that you have, so this is sort of attempted to be shown in this sort of sketch here. So if you have the core component, which is effectively sort of spinning slower, if you like, or at the same speed as the observed component, and the superfluid component spinning much faster, then you get this coupling where you get a fast locking to the superfluid component, which overspins you, and then you lock onto the core, which spins you down. But there's definitely a sort of, a huge amount of free parameters there, which is, well, if the core was spinning faster still, then you would sort of shoot up and then shoot up again. So yeah, you're adding new parameters, and so you can fit most things with a 3-component model. You just need a few extra parameters. But at the same time, the physics tells us that this is probably quite likely.
Greg?
Yeah.
I don't know if this is a relevant question, but is there any reason to think about conservation of spins or angular momentum?
You absolutely have to conserve angular momentum between these things, yeah. And that's, that's part of solving the theorists who come up with the models of this. Part of solving those models is you need to conserve angular momentum here. But
can I see it in this plot?
So what's sort of missing here, you're looking at the rotation speed, but you're not seeing the moments of inertia as well. Now, the plot is just a sketch done by an artist. I can show you the models which we have do conserve angular momentum.
Okay.
I mean, I guess, gone too far. I guess if you want to sort of, hand wavy sort of point is that, so your lower line here and your upper line, your final line must be between these two in order to conserve angular momentum. Otherwise, something strange would have happened.
Okay, and all of them, or all of them are in the same direction, I believe, right?
Yeah, exactly.
Okay.
Okay, so so the overshoot seems very compelling. There are and therefore the physics of the idea that there's probably 3 components in the star. Theories told us that for a while, but this is, I think, the first evidence that we have that tells us it's more than likely there. There are a couple of models out there which could also explain the overshoot in terms of other sort of physics going on. Again, those are still sort of being debated, and I think that it's going to be interesting in the coming years to see which of these sort of bears out, and particularly with future observations, which are going to make this more interesting. Right now, we may not be able to sort of tell between them from the data. But on this plot here, there's a second curve which I've added, which is this red one here. And you'll see that this has a very funny feature to it, which is that about 100 seconds before the glitch, it suddenly decreases in frequency. Now, why is it doing this? Well, this is what I was mentioning about the dangers of building phenomenological models. Is at some point you sit there and you go, well, in that gray plot, I can see something going down. So let's play around with our models and see what happens if we add in a little step down. And that's exactly what we did. And we found pretty strong evidence in support of the red model over even the blue model, okay? But there's a danger here, right? Which is we're not at all being guided by physics. So with the overshoot model, we were being guided by the physics, but with this, there was really no reason to do it other than we felt like it, right? And so this could very well be sort of p-hacking, if you like. This model could be complete nonsense. But nonetheless, there's evidence there. So
let's just tell people what p-hacking means.
Okay. So p-hacking is a process which is done, well, there's been a lot of controversy on it in the social sciences, in particular in the last few years. And the idea is that you, so if you do an experiment, you set up some experiment and you say, I'm looking for some effect. And if you get p less than 0.05, then you can say that, and that's so p being the probability that the effect is not there compared to the null hypothesis. So a standard sort of p-value, if that makes sense. Are people okay with the p-value?
You're gonna have to answer, guys, if you know what a p-value is.
I don't.
Okay, so let's take the gravitational wave example. I hopefully people are familiar with the gravitational wave sort of distribution, right? So you see you look at the background distribution by time shifting all of your events, all of your data, decohering it against each other. You end up with some distribution, and you then effectively you go and look at your event and you look at the SNR of it or whatever your detection statistic is, and you look at where that sits in your noise distribution. And what you're sort of doing is you're effectively asking the question, how likely would I be to see this particular value if there was no signal and I was looking at just random noise from my detector? And so your p-value is basically the probability of seeing this thing in just background noise. So small p-value means you have seen something real, right? So this is frequentist statistics at its core, is you find a small p and you say, oh, that means that I can refute the null hypothesis. And then terribly what you can say that therefore the effect I was looking for is real. So p-hacking.
I'm just gonna intervene here and say that, first of all, this is what happens when theoretical physicists start to do data analysis, and they realize that a theoretical physics degree teaches probability in the quantum context, but doesn't actually teach statistics. So for a couple minutes on statistics, imagine I have a coin, a regular two-sided coin, and I tell you that I can predict what the coin will show when I toss it. And I say, when I toss it, it's gonna turn out heads. And then I toss it and it turned out heads. Will you believe me that I can predict the coin? Will anyone believe me that I can predict a coin toss if I call heads and then it falls on heads?
No.
No.
No. What if I give you a sequence of 20 results, 20 outcomes? I toss the coin 20 times and it comes exactly as I said. Then will you believe me?
Then I would follow you to the grave.
that would be a good intuition, because 50% tosses are 2 to the 20, which is about 1 in a million chance. So, okay, maybe not to the grave, but you might trust me with a small investment at Vegas or something. And the difference between those is a p-value. The chance of me getting it right without actually knowing, randomly out of noise getting it right, is 50% for one toss. But the p-value for 20 tosses is 1 in a million, which is a very small number, or say it's a small number, enough for you to trust me that there is a signal there, that I know what I'm talking about. P-hacking is if I were to toss the coin 20 times, look at the results, and then tell you, this is the result of these 20 coin tosses, after I already saw the results. Then would you trust me? Would anyone trust me at predicting coins if I toss them first and then tell you the answer?
No.
No. Okay, so often p-hacking is a bit more subtle. It's not as obvious as this, but I could say something like, if the coin came out 15 times heads and 5 times tails, I might tell you, I think this coin has a preference for heads over tails. And it matches the answer, so you might think I got it right. But if I did it after seeing, then I can basically, conjure up whatever statistic I want to claim that might look convincing, but it's still meaningless if I did it after seeing the data. So p-hacking is basically a warning not to fit your models too well after you saw the data, because whatever p-value you claim to have after that is really completely meaningless. Back to you, Greg.
Thank you very much. As a nice statistics aside, I always enjoy them. So yeah, so we had some concerns ourselves that we were kind of model digging here at p-hacking and trying to find something, but nonetheless, it does seem like it's there. Now, one thing you can do in this circumstance is you can go and look at other sets of data. And it turns out there is another set of data for this, this pulsar. So before they had the nice Mount Pleasant observatory, they had a smaller dish which tracked the Vela pulsar, and they did see a glitch with that. And there is some evidence in that there is also this precursor slowdown, but it's very tentative because the data just wasn't as clean and nice to study. So we're yet to say whether this thing is real or not. The ultimate test will be, we need to see another glitch and see if this feature's there, then we'll be happy, and we'll be happy to say that this is a real feature. But until then, we're not sure. Now, one of the big problems, right, and the reason that we worry about p-hacking is there's no good physical model for what happens here. So there's been some models come up in the literature since we published this, saying that it's consistent with the formation of a new superfluid vortex trap. Ofek, please don't stop me to ask what that means. That paper has been printed out and scanned over about 100 times by me, and I still don't understand the details of it. So it's an ongoing battle to try and understand what these vortex traps are. But there's the real problem is that you need a huge, still a significant portion of the moment of inertia to make it work, and you need it to go both ways. So it was hard enough to make a glitch, and that we needed two components to couple, but now we need, another, maybe a fourth component, right, which is slow, much slower than the others, or something like this. And so you start to get down this road of just kind of digging into models, and we don't feel very confident at this point to do that. But there's, tons of questions you can ask, like, does the slowdown itself, is that maybe the trigger to the glitch? But then what triggers the slowdown? And is the slowdown perhaps related to the crust quake? All of these things are to be investigated. I don't have good answers to them. But at the end of sort of, so when we put out this work, we got a lot of interest on it, but we got a lot of interest from radio pulsar astronomers who sort of pointed out to us that, well, actually, maybe this isn't a slowdown at all, but it's just an artifact of your data analysis. Now, I'm aware that I'm coming up to time. Are we okay to go a little bit longer, Ofek, or?
Sure, a little bit, no problem.
Okay, I'll try and go as fast as I can. If people need to leave, then that's absolutely fine. So a little bit of an aside on traditional radio pulsar. Actually, let me ask so I can know how much longer are you happy with? 10 minutes? 15?
How much do you need?
If you give me 10, I think I can get through everything with some detail without rushing too much. Okay. Sure. So radio pulsar timing, the method that you use, for people that are used to sort of looking for CBC signals, this will be somewhat familiar. So what you do is you use match filtering. You come up with a template, but the template in pulsar timing is completely fixed. You effectively take a very high SNR look at what a pulse looks like, and you take that as your template. So there's no free parameters whatsoever. You then shift that thing up and down, so you slide it back and forth against the data, and you measure the signal to noise ratio of that of the match filter. And when there's a peak, you then say, that's my time of arrival. So that's how you measure the time of arrival of your pulses. And that's really the raw data of pulsar timing, is just those time of arrivals. The problem with this is that if you have sort of changes in the pulse shape, so if the data changes here, but your template doesn't, then what this manifests as changes or systematic changes in the arrival time. So things that you think are related to the dynamics can actually be related to the changes in the pulse profile itself. So perhaps, the second edge gets sort of bigger, or you get another peak popping out on the right, or something like that. So this is a concern, and if real, it would, sort of scupper our chances of, having a slowdown. But it may be interesting in that, perhaps the pulse shape changes just before the glitch, and that in itself could be interesting. So what we wanted to do was to go and study this and say, okay, can we, figure out, is it a real slowdown, or is it changes in the pulse shape? So what we did was we used what's called profile domain timing. And this method, what you do is, rather than just match filtering a single template, you actually fit each individual pulse with a shapelet based model. So this is, again, an analogy to gravitational waves. If people are aware of the sort of models which use chirplets and things like this so there's a Bayes wave algorithm is what it's called, to try and fit, gravitational waves with a sort of phenomenological model. This is the equivalent, but for radio pulsars, and we used many of the methods were inspired by the Bayes wave code. So huge kudos to them for inspiring us with this. So we built this code. It's called Kookaburra. The code is available there if anyone wants to play around with it for fun. And we fitted it to all of the available data. So we took about 30,000 pulses around the glitch. And what we found was, spelling typo there, we found no evidence, not no evidence, for systematic pulse shape changes. Okay, so we effectively studied what the pulse shape did during that period. And what we found is that there was no obvious sign of something happening which would cause that slowdown to happen. Now, this was a bit sort of disappointing, and almost like a null result, which we sort of couldn't do much with. But it was interesting. We wanted to write it up and things like that. So we started going through the process of writing it up and saying, well, we can't readily explain this anti-glitch beforehand with pulse shape changes. During that process, we sort of stumbled on something else, which is kind of more interesting, which is that when you apply this profile domain method, you're fitting a model to data. And so whenever you do that, you can calculate a Bayes factor if you come up with a second model. The second model here is a null model, which is that there's no pulse in the data. So we have two models, given some data set, you have two models. One is that there's a pulse in there, and the second is that there's no pulse. And we can calculate, therefore, a Bayes factor for the pulse versus null. And originally we started sort of building this just because we wanted to confirm the existence of that original null 77, pulse 77, which I told you about earlier, which Jim found. Now, this is what happens when you look at data away from the glitch. So this is about 85 days beforehand. You look at the Bayes factors, and what you find is that they are extremely large, very strong signals. So these are huge SNRs if you want to convert this to an SNR. SNR about 100 or so. Now, okay, so then if you then go and look at data around the glitch, what we see is this. So the glitch occurs right here. So this is time 0. Pulse 77 is this one down at the bottom here. And so that we readily identify as the null from the Palfreyman paper. But what we also see is a whole bunch of other things which sit in the sort of gap between the strong signals and the null. And these things we term quasi-nulls. And we term them quasi-nulls because they're not as strong as the null itself. There is something there, but it's definitely a lot weaker. And I can show you this to you directly from looking at the data. So these are 4 of the quasi-nulls, which I picked out. So that the orange line here, the orange line you're looking at is a time average, and the blue is the raw data. And so you can see there's a sort of slight bump in some places. But if you look at what typical pulses look like, which are these are just some random pulses I pulled out of the same data set, it's definitely not as strong. Okay, so those are regular pulses. These are these quasi-nulls.
Can you go back one?
To this one?
Yeah. Is any of these, or can you identify pulse 76 in this plot, or approximately where it will be?
Yeah, pulse 76 sits up in the bulk here, so it is a strong pulse. You can look at measurements of, we have a measure of the width of the pulse, and that in that plot, it's a huge outlier, but it's the only outlier, and none of these other quasi-nulls are sort of preceded by a broad pulse or anything like that.
You did an independent search for broad ones as well.
Exactly, and there are, so the broad pulse isn't as statistically significant as the null. It sits out as an outlier, but there are other broadly, there are some other broad pulses in there as well. So it's really the combination of the broad pulse and then the null which makes the broad pulse interesting. Okay, so we termed this flickering. So we termed them sort of quasi-nulls as the individual thing. And then our sort of claim is that, well, if we look at, what's going on here is, well, we're not seeing a strong sort of pulse consistently from this, from the Vela pulsar. We're seeing it sort of almost flicker in and out every now and then. Nice. Okay, so yeah, I'm 5 minutes over, so let me get to the sort of finishing thoughts here. So what do the quasi-nulls tell us? Well, they are a huge issue for the Bransgrove picture of the null and the glitch together. And the reason is that in the Bransgrove picture, you had a crust quake happening deep in the core, and the crust quake explained the null, and then it also explained the glitch. Now you could, sort of modify it, and maybe you have lots of crust quakes, right? Like a sort of series of crust quakes, but only some of them cause the glitch, right? And maybe it makes sense that the largest crust quake, which disturbed the magnetosphere the most, also triggered the glitch. Or perhaps that wasn't the case, and there's just a sort of series of crust quakes which then resulted in the glitch. All sorts of things need rethinking with that, and we've talked to Ashley and others. Yuri Levin in particular is very interested in this and trying to figure this out, because this adds a new dimension to the challenge for the theorists. Now, of course, it could be right that the nulls are nothing to do. That the nulls trigger the glitch themselves, right? There could be, there's sort of a correlation or causation arguments to go on here. Is it the crust quake which comes first, or perhaps it's the nulls which come first, and magnetospheric activity, some sort of thunderstorm, if you like, which then causes the glitch. Of course, thunderstorm in air quotes, because there's no physics there. We're just sort of waving our hands around. Okay, so the quasi-nulls make this a lot more interesting, and so I can get on to now where the challenges are, right? So the Vela glitch gives us this amazing opportunity to study the interior of the neutron star, and so far it's thrown up already a huge number of challenges to our conventional wisdom. I think the one thing that I feel pretty confident about is the evidence for the 3 distinct components in the neutron star. I've yet to see another model which can explain that feature and as well. But okay, this could be, I wouldn't bet my house on this yet, but it seems to be the one thing which you can take away from all of this and say that seems very strong, is that there is an overshoot. But the mysteries now come in understanding these nulls and these quasi-nulls and their relation to the glitch, and also whether this precursor is physical and whether it has anything to do with glitch itself. So where do we need to go now? Well, the Vela pulsar fortunately will glitch again. It glitches roughly every 3 years. Some of you, the observant among you, will say, well, it should have glitched last year, and indeed it did. Unfortunately, Jim wasn't ready. So Jim Palfreyman was not ready in observing mode and didn't catch it. There is a lovely story that this was caught by an amateur radio astronomer also in Australia, a guy called Steve Olney, who literally has a dish out the back of his house, which also tracks the Vela pulsar. And he was the one who first found this glitch, but with his instrument, it's just nowhere near sensitive enough to do anything interesting, unfortunately. But it's going to glitch again in about 3 years. So about 2022, we'll see it once more. And of course, there are other pulsars out there that we could catch glitching. Now, the thing is, though, is we need to see them, we need to observe them during the glitch. And the quasi-nulls then offer a really interesting opportunity, which is that they occurred up to a few hundred seconds before the glitch itself. And we haven't actually managed to say definitively how early they happened. So we need to analyze more data, and that's ongoing at the moment, to say, when the first quasi-null happened before the glitch. But perhaps they, may go up to 10 minutes or so. And if that's the case, then one can imagine having a kind of early warning system hooked up to the Mount Pleasant Observatory, which, as soon as quasi-nulls start going off, then goes and tells, say, the Parkes Observatory or Jodrell Bank to spin around and look at the Vela pulsar. And with something like the Parkes or, even SKA, which will be online pretty soon, we will get a much clearer picture of this. And if you saw this through the SKA, we'd be talking a whole different level of sort of the observations that we'd have. So that's, I think, something that's really exciting and could be very intriguing going forward. The final thing I'll just throw out there is sort of, I know we have a gravitational wave crowd here.
Is there also a point in having a follow-up? So if you see a glitch, point other telescopes to it to catch the flickering or whatever afterwards?
Yep, so we saw quasi-nulls after the glitch itself. And so again, we don't know the exact time scale, but yes, certainly still worth looking at it just after. That will still give you information and better constrain those parameters of the glitch itself. So always worth, the more observations we can get, the better for sure.
So how expensive is this telescope by this Steven guy who seems to be able to just operate an early warning system on his backyard?
So that, I mean, that's not very expensive. I think probably a few tens of thousands of dollars he's probably spent on it, but that's not sensitive enough. You would need something like the Mount Pleasant, but there are a lot of dishes out there that are about that size. There's, radio astronomy is a huge field, and as the dishes get bigger, they don't get rid of the old ones, so they just sit there. So I think there are opportunities, but I think the Mount Pleasant one is well set up, and all it really needs is a computer hooking up to it, which does online analysis and is quick enough and somehow hooked up to a scheme of telling other radio pulsars observers to turn their dishes around. So then the final thing I wanted to mention was just that there are some models out there which say, well, okay, if you've got plates moving around inside the star, and dynamics happening on sort of tens of seconds or tens to hundreds of seconds timescale, you could imagine that this produces transient continuous gravitational waves. So that's a sort of oxymoron in itself. So transient continuous means it really means a transient gravitational wave which lasts something of order 100 to 200 seconds or so, but has a roughly constant frequency over that time. So people in continuous gravitational waves always sort of refer to these as transient continuous gravitational waves because their methods of finding the signal would be the ones that you'd use, because they, especially if it lasts a few hundred seconds or so. What I will say is this is hugely tentative and highly unlikely, but at the same time, the LIGO detectors were up during the glitch. I know some people have done some preliminary looks and not seen anything. It's probably not sensitive enough to see anything, but it's there. It's a possibility and could tell you something interesting. But I think, we have opportunities going forward, and I think the next glitch, so 2022, is going to be a really interesting time to figure out which of these phenomena hold out.
We should not leave people with the idea that there will be a glitch in 2022, because as we said, it's a Poisson process. So the glitch could be tomorrow.
It could, so Vela is this one, which is slightly quasi. It's not a pure Poisson process. It comes more regularly than the others, but yeah, it's been roughly every 2 to 3 years, pretty consistently. So yeah, we'll see.
Okay, thank you.
No problem. Thank you all.
Any other questions from anyone? Well, pulsars, radio astronomy, statistical analysis of data, how to make money in Vegas.
So I think we had really excellent questions. That was really nice, and I apologize for going over, but it was well worth it to get into some of those details.
Anyone? Okay, if not, we'll wish you a happy new year. Wish the folks over here an easy lockdown.
Yeah, we're in lockdown as well, so I feel your pain, and I hope we all get through it before too long.
Hopefully. And we'll wait to see you and welcome you at the physical seminar here whenever that's possible.
That sounds wonderful. Thank you all very much. And if anyone has any follow-up questions, feel free to email me, of course. Take care, everyone, and stay safe.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.